Namaste everyone. Today's class will be an introduction to electromagnetic induction. As seen on your screens, our objective would be to understand the principle of electromagnetic induction, and we will try to see a simulation of electromagnetic induction using a bar magnet, and we will see what are the factors that are going to affect electromagnetic induction. Now, you see a coil of wire here connected to a bulb and a meter that reads the presence of current. In general, this is a galvanometer that will be connected. Now, you can very well see here that there is no voltage source that is connected to the bulb. It's only a meter that is going to detect the presence of current. So if I am going to bring this bar magnet closer, watch very carefully. As I am moving the bar magnet closer to the coil, you see that the bulb glows. But the bulb stops glowing and the indicator stops deflecting the moment the movement of the magnet stops. Let's see one more time. Put your eye on the bulb and the meter. Now I'm going to move the bar magnet. As I move, the bulb glows. As I stop moving, the bulb stops. I start to move again, the bulb glows. I start to move again, the bulb glows. Now watch another thing. All through now I was moving the magnet into the coil. Now look at the direction in which the indicator will move when I try to move the magnet out of the coil. Do you see the bulb still glows, but the direction of the deflection in the meter is opposite to the previous case. I'm going to move out again. It goes to the positive side. I move out, positive. I move in, it is negative. Out, positive, in, negative. So the direction of the current is changing if I change the way in which I move the magnet. Closer it moves in one direction, while farther it moves in another direction. Now let's do one more thing. Let me change the polarity of the magnet. Do you see that? When I change the polarity of the magnet, for that moment when the polarity changed, there was current in the circuit. Now I move out, it goes left, and I move in, it goes right. That means the direction of the current has changed with respect to the polarity of the magnet also, right? Let's look at one more thing. I'm going to move the magnet slowly. Do you see the way the bulb is glowing? You can see the intensity of the current. Now let's say, did you see that, children? When I moved the magnet faster, there was a greater amount of current. Now let's have a look. I'm going to move in at a very fast rate. Wow. Do you see that? As I move in faster, the amount of current produced is greater and the deflection in the meter is full scale deflection, right? As I move slowly, you see that the deflection is not full scale. So the magnitude of the current depends on the speed with which you move the magnet, right? And one more thing let us see before I will go into it. Now I'm going to show you two coils. One has only 2 turns while the other has 4 turns. Now let me move in, right? Let's move in. It's a very bright light with the same speed. If I'm going to move in, do you see that the intensity is not as much as it is in coil with 4 turns? That means greater the number of turns, greater is the magnitude of the current that is going to be flowing in the circuit. Now one more thing let us notice here is this. What is causing the current flow? When there is no battery connected here, when there is no voltage source connected, the bulb still glows. That is what is the principle behind electromagnetic induction. When the magnet is moved, as the magnet is moving, what is happening? Let me put on the field lines. The magnetic field lines associated with the coil changes. So as long as there is changing magnetic field associated with the coil. Get this very clearly. As long as there is changing magnetic field associated with the coil, there will be current that will be produced in the closed circuit. The moment the change stops, when I stop the magnet, there is magnetic field associated with the coil, but the magnetic field associated is not changing. It's a constant field. Then there will be no induction. So as long as there is a momentary deflection, if you see, there is a momentary deflection when there is a change. When the change stops, the induction of the current stops. So that's electromagnetic induction. The inducing of current in a closed circuit when the magnetic field associated with it changes with respect to time is what we call as electromagnetic induction. This is a simulation that is taken from the Colorado University simulations, which are free for learners to download and experiment on, right? So if we move into the outcomes for today's class, you should have understood what is meant by electromagnetic induction. That is inducing current by varying the magnetic flux associated with a coil in a closed circuit. And we saw a couple of factors here. One is increasing the number of turns. It changes the magnitude of the current, and changing the way in which you move the magnet and changing the polarity of the magnet decides the direction of the induced current. Also, we looked at the definition, which I will state once again, is inducing current in a coil by changing the magnetic field associated with it is called electromagnetic induction.